Now we want to take a look at logical relationships that happen between pairs of sentences. And you'll notice that the book covers 4 different types of logical relationships between pairs. A pair of sentences can be consistent, inconsistent, contradictory, or logically equivalent. And I want to start by just running through what each of these things means. To say that a pair of sentences is consistent just means that there's at least one assignment where both sentences are true. And to say that a pair of sentences is inconsistent means that there is no such assignment. That is, there is no assignment where both sentences are true. There could be assignments where both are false, but there are no assignments where both are true. To say that a pair of sentences is contradictory means that they are the opposite on every assignment. And that's more than just inconsistent. That means there's no assignment where both are true, and there's also no assignment where both are false. If one is true, the other is false. And finally, to say that a pair of sentences is logically equivalent means that they are the same value on every assignment. They have the same truth value on every assignment. And notice how this means any pair of sentences from our system that you pick will be either consistent or inconsistent. They don't have to be contradictory, and they don't have to be logically equivalent either. They may or may not be one of those things. Now, I want to pay special attention to the last possibility, that you have a pair of sentences that are logically equivalent. That's going to be more interesting to us than some of these other possibilities for various reasons. And I want to start by taking a look at kind of a trivial example. Suppose we're comparing the statement A with the statement not A. This is probably another one of those situations where you don't really need a system to tell you that these two statements are going to be equivalent. It's the same thing. I mean, this corresponds to something like a statement, Al is home, is A, and then the other statement is like, it's not the case that Al's not at home. So those even sort of seem like they're just saying the same thing. You hardly need a system to tell you that. But nevertheless, let's see how that works out within our system. We compared the two assignments for A. We have the assignment where it's true and the assignment where it's false. And of course, tilde A, the values are the opposite of the values for A. And then the values for the negation of that are the opposite of it. And so that, of course, returns us to the original values, the same as the values of A. True on the first assignment, false on the second. So that's what we mean by saying that these statements are logically equivalent. They have the same truth value on every possible assignment. In this case, there are just 2 possible assignments. They're the same on the first assignment and same on the second assignment. Once again, it's not always going to be immediately obvious that the sentences you're dealing with are logically equivalent. So if you have a pair of sentences like, say, P wedge R, and then we're comparing that to the sentence tilde R arrow P. And again, let's read these off as what they're saying. The first is P or R. The second is if not R, then P. So the first thing we're going to want to do is set these sentences up together on a truth table. So we have P or R on the left side, not R implies P on the right side, and we want to make sure that we keep these separate. And we'll set up our assignments, this time I'm not going to write down the assignments off to the left. I'm just going to write the assignments directly underneath the sentence. And I'm going to start on the right here with P, and I'm going to alternate true, false, true, false. Now I have to make sure that I assign P the same values across the table. Remember here, the point is that we're comparing assignments for P and R. So if P is assigned true here, then it has to be assigned true also everywhere else it appears on the table. So we need the same values for P over here on the other side of the table. And then when we come to R, we will alternate by doubles. So true, true, false, false. Once again, same values for R everywhere it appears on the table. And now I will just go through and compute the truth values for the sentences on every assignment. And when I'm done, I'm going to compare the ultimate value, which is the value I get for the main operator, on the left and on the right. So the sentence on the left is easy enough. It's only one operator. The operator is wedge, and that is true when at least one side is true. So the values I get are true, 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 and false. It's only false on this last assignment where both sides are false. Meanwhile, on the right side, I start with the tilde. Remember, tilde comes before anything except parentheses. And I do the opposite of R. So I'm going to get false, false, true, true. Cross out the values for R because I don't want to look at those when my left side of the arrow is what I got under the tilde. So now the rule for the arrow or horseshoe is it's only false when the left side is true and the right side is false. So first assignment, the left side's false, so it can't be false. It's got to be true. Second assignment, the left side's false again, so it's true once again. The third assignment, the left side's true, but the right side's also true, so that's also true. And on the last assignment, the left side's true and the right side is false. That is the case where the arrow or horseshoe is false. So now I have the final result on the left, sentence on the left. I have the final result for the sentence on the right, and I just compare the two. Are they the same on every assignment? Yes, they are. True, 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 false. So these sentences are logically equivalent. And that's a result that I bet you didn't just expect right away when you're looking at those two sentences, that P or R turns out to be the same thing as not R. If not R, then P. Now, this relates to something from 6.1 as well. When we were symbolizing statements involving unless, which when we're building up our system, we didn't necessarily plan to be able to represent a statement using unless, but it turned out that we could. And you may have been puzzled when in the book it told you you can just take the word unless and replace it with wedge. So if you have a statement like, we'll have a picnic unless it rains, and the book tells you you can just take that word unless and replace it with wedge. And I always thought that was kind of strange. We'll have a picnic unless it rains is represented by P wedge R. I mean, P wedge R is P or R. So either we have a picnic or else it rains. What seemed more natural to me is to think of unless as saying if not, right? We'll have a picnic unless it rains means if no rain, then picnic. And if not signifies a conditional statement where the antecedent is negated. Remember, if signifies the antecedent, and then we have not, so that's negation. So that signifies to me, I would think of this as an arrow statement, and on the left side of it we have the negation of the statement it rains, so tilde R, and then on the right side of the arrow we have P. So we'll have a picnic unless it rains. It seems natural to me to think of that as if it doesn't rain, then we'll have a picnic. And by the way, remember, if I say if it doesn't rain, then we'll have a picnic, what am I saying about the case where it does rain? Nothing at all, right? I only said that if it doesn't rain, then we're having a picnic. It's possible that if it does rain, that doesn't mean we're not having a picnic. I didn't say what would happen if it did rain. You know, I could say, if it doesn't rain, then we will have a picnic. And then you say, and what if it does rain? And I say, well, if it does rain, by God, we'll have a picnic anyway. In any case, the second representation, the tilde R arrow P, seems more natural to me as a way of representing we'll have a picnic unless it rains. And then in the book, it says you can represent that by saying P wedge R. So what's going on there? How can there be two ways of representing this sentence? Well, here's how. Those two sentences are logically equivalent, and either one seems natural enough as a representation of the unless statement. So we can just think of it as we have two ways of representing the unless statement. One is sort of more natural, in my opinion, tilde R arrow P, but the other one is operationally much simpler. You just replace unless with the wedge. And they are logically equivalent, as we can see from our truth table above. They have the same truth value on every assignment, no matter what. Now, it's certainly worth taking a look at some of the other categories that pairs of statements can fall into. They have to be either consistent or inconsistent, and they may be contradictory, but it's going to be more relevant to other things that we're doing to say whether sentences are logically equivalent or not. So I'm going to focus just on the logically equivalent category, and that's the only one that I'm going to put on the test. But like I said, it's not a bad idea to take a look at the other categories as well.